now that we know something about the rank of a matrix, we can actually use that to understand something about solution spaces for homogeneous systems. So if we have a homogeneous system, remember we can represent this homogeneous system purely based on its matrix of coefficients, right? We don't need to write down an augmented matrix because the augmented column is always 0 for a homogeneous system, so there's no point in keeping track of it, right? So if we have this matrix that represents a homogeneous system, we could ask what its rank tells us about the solution set for this homogeneous system. Well, remember how we solved homogeneous systems. We did row reduction to get some reduced row echelon form, and then we turned that into, we used the reduced row echelon form to describe the collection of solutions. So if we have a reduced row echelon form, there's going to be this stair step of pivots. Everything below that is 0, and right, something like this. And let's say that the rank, so the rank of this matrix, it is what it is, but remember the rank, once you've reduced row echelon form, the rank of a matrix is just the number of pivots. So number of pivots in reduced row echelon form. Okay, and this matrix, it has n columns because, well, just because that's what I've called the number of columns. Okay, so question, well, so we know that the solution sets for homogeneous systems looks like just a span of, certain vectors like this. So we don't know how many. Okay, so the solution set looks like this, but how many vectors are there? Well, it depends on the number of free variables, right? What we've seen is the number of vectors that you need to span the solution set is just the number of free variables. So vectors to span the solution set. Right, actually, the number of vectors you need to span the solution set, this is the dimension of the solution set. Right, because we know we can make the vectors spanning the solution set, we can make them linearly independent. So the number of vectors, how many vectors do we need to span the solution set? Well, it's just the number of free variables, right? The way that we parameterize solution sets for homogeneous systems, we always have the same number of linearly independent vectors as we do free variables. So the number of vectors we need to span the solution set is just the number of free variables. Well, how many free variables are there? Well, if you look at this reduced row echelon form, free variables correspond to columns that don't have pivots. So this is the number of non-pivot columns. And how many non-pivot columns are there? Well, there's n columns total, and the number of pivots is the rank of A. So the number of non-pivot columns is just n minus the rank of A. So the size of solution sets is actually determined by the rank of the matrix. And this is something that isn't obvious, really. Rank is, originally we defined it as the dimension of the row space. And it's not at all obvious that, the collection of solutions to this system of equations has anything to do with the row space of this matrix. But in fact, the dimension of the solution space is just n minus the rank of the matrix. It's really this that makes rank important, just to give something away. All right, so knowing this about this relationship between rank and dimension of solution spaces lets us sort of pull together a lot of different threads involving solution spaces and rank. So, for example, right, all of these statements are actually equivalent. So if you have a rank of matrix n, that's the same thing as the matrix being non-singular. So what non-singular means is that the homogeneous system with A as coefficients has a unique solution. And if it has a unique solution, that means the solution has to be 0. So if the rank is A, right, so let's prove that 1 is equivalent to 2. So the dimension, let's look at the dimension of the solution set for the homogeneous system. Well, we know it's n minus rank of A. That's what we proved before. So the dimension of the solution set is 0 exactly, so if and only if with 2 f's is an abbreviation for if and only if. So the dimension of the solution set is 0 exactly when, if and only if, the rank is n, right? The only way to make this difference equal to 0 is if the rank is n. So the dimension of the solution set is 0 if and only if the rank of A is n. But how could the dimension of the solution set be 0? The dimension of the solution set is 0 if and only if the solution set is just the 0 vector. But the solution set is just the 0 vector if and only if A is non-singular. So now we see that A is non-singular if and only if the rank is n. So we've shown that these two, 1 and 2, are equivalent. All right, so what about the rows of A? Well, the rows of A are linearly independent if and only if the rows are a basis for the row space, if and only if, so I guess let me write this out. So here we're showing 1 is equivalent to 3. So rows are linearly independent if and only if rows, all rows together are a basis for the row space. And I should have said this at the beginning, but this is something for square matrices only. So our matrix is n by n. So the rows of a matrix are a basis for the row space if and only if the dimension of the row space is n. And remember, this is the rank, and the dimension of the row space is the rank. So now we see the rows are linearly independent if and only if the rank is n. All right. Now showing that 1 is equivalent to 4, the columns of the square matrix being linearly independent. So showing that these are equivalent, it's actually exactly the same as showing that 1 is equivalent to 3, except wherever you see row, write column. So right, the columns are linearly independent if and only if the columns serve as a basis for the column space, if and only if the dimension of the column space is equal to n. But the dimension of the column space is the rank, so we're done. All right. Now maybe a more surprising thing is that the rank is n if and only if every system with A as coefficients has a unique solution. Now this is saying a totally different thing than number 2, because number 2 is talking only about homogeneous systems. So to show that 5 is equivalent to all of these, what I'm actually going to do is show that 5 is equivalent to 2. Right? So if we have a non-homogeneous system, write down its augmented matrix like this. So our matrix A, the matrix of coefficients, is most of this augmented matrix, and then the augmented column is the right-hand side of the system. So if we row reduce this, what do we get? Right. Remember that this part of the matrix is n by n. What do we get? Well, we get 1s on the diagonal if and only if A has rank n, right? Since there are the same number of rows and columns, the only way to have n rank is to have a pivot in every column. So I guess this is, we're showing that this is equivalent to 1. Okay, and then we get some thing over here. Okay, but you get this for your augmented matrix if and only if you have a unique solution. So we're done. You have a unique solution if and only if your augmented matrix always reduces to something like this. But this happens if and only if your matrix has rank n. So we're done. Now this shouldn't come as any surprise, I guess, because if a matrix, we know that a solution to a non-homogeneous linear system always looks like a particular solution plus a homogeneous solution. But that's solution. But if our matrix is rank n, then this homogeneous solution has to be 0, and so you can have at most one solution, right? Maybe the surprising thing about this situation is that not only can you have at most one solution if the rank of this square matrix is n, you actually always have a solution, right? So we're getting a little more for free with this.